Madam, I think we can start. So let me introduce. So good morning to all. Welcome to the Silver Jubilee lecture series of the International School of Photonics, CUSAT. And this is our very first talk, and we are honored to have Professor Kyoko Nozaki from University of Tokyo here with us. Let me welcome the Director of International School of Photonics, Professor Dr. Pramod Gobinath, to introduce the speaker.
Thank you, Dr. Praveen. I think a very warm good morning to all of you. We at the International School of Photonics, Kochi University of Science and Technology, are very happy to invite all of you to the Silver Jubilee lecture series. As the name suggests, the International School of Photonics has completed 25 glorious years of academic and research excellence. And as a part of celebrating it, we have organized a series of lectures by veterans scientists all over the globe, showcasing state-of-the-art research in potential streams of optics and photonics. We are extremely privileged and honored to be beginning this Silver Jubilee lecture series with the esteemed presence of the most distinguished professor and scientist from the field of organic chemistry, Professor Kyoko Nozaki from the University of Tokyo, leading a dynamic group in organic chemistry, the main research interests of which lie in discovering, developing, and understanding new reactions mediated by homogeneous catalysis for organic and polymer synthesis. The key areas of research interest of the Nozaki group also extend to catalytic transformations, functional polymer synthesis, synthesis of aromatic compounds, and heterogeneous catalysis. Professor Kyoko has been awarded the Ohm-Coase Prize in Organometallic Chemistry in 2004, Wiley Award in 2008, Saruhashi Prize in 2008, Mukiyama Award of the Society of Synthetic Organic Chemistry, Japan, Catalysis Science Award, 2009 Nagoya Silver Medal, 2013 Schlenk Lecture Award, and a lot of other awards too. Professor Kyoko is delivering a talk on synthesis and properties of heterohelicenes. Once again, on behalf of all of us at International School of Photonics, CUSAT, I welcome you, ma'am, to deliver the talk. I also welcome all the participants to the first webinar series. Thank you.
Thank you very much. Yeah, thank you very much for your kind introduction. Good morning, everyone. It's truly my honor and pleasure to start this very prestigious lecture series. And as the chair kindly introduced, my research topic, my research area now is not exactly photonics. Actually, when I got invitation, when I first met Dr. Praveen, who organized this conference, it was 2016, a meeting for CO2 utilization. And he was interested in our work, that's CO2 and hydrogen to produce formic acid. Formic acid is a main content of ants' acid. But whatever, we are working on iridium catalyst and how the organometallics work for catalysis is my interest, and it was Dr. Praveen's interest at that time. And then I got invitation from him, would you like to give a talk? And I said, sure, why not? And then what he said is, since the specialization of the department is photonics, any topic related to spectroscopy would be appreciated. And he said, what, I'm synthetic organic chemist and I'm working on catalysis. But as it's such a great honor and opportunity, I will do my best to focus on this type of area. So as you can see, this is the homepage of our, this is the website of our research. And So if you're interested in, you can visit this website later on to see what we are doing, like homogeneous catalysis for catalytic transformation, like CO2 utilization, or to make polymers, or to utilize biomass, so on and so on. And today I decided to select this talk, that is synthesis and properties of aromatic compounds, because I thought this would best fit to the audience interest. I just, okay, so let me move on to my topic. I will focus on helicene synthesis. What is helicene? Helicene is a molecule shown here that forms a helical form. This part is coming up to front. We draw like this in organic chemistry, and this part is buried behind, so that this structure is not planar, it's helical. So I just briefly mentioned about its synthesis, and then we'll go forward for its absorption and emission properties, which is very much related to photonics, and also go forward for chiroptical properties for some molecules. Helical structure is everywhere, like DNA double helical structure, or peptide forms helical structure, or sugars like starch also form helical structure. So there are so many helical structures, and I think helicene is one of the most simple helical organic molecule. As you can see, benzene rings are fused to minimum 6 of them. So the terminal position over here, the CH, and this terminal position, CH, cannot overlap. So it forms helical structure. Helicene has chirality, so-called minus and plus. M stands for minus, P stands for plus. And plus means the right-handed screw, and minus means anti-clockwise screw. And the properties, and as you can think of, it's chiral. Chiral means handedness, that two mirror images do not overlap each other. And it's chiral. It shows in absorption, either left-handed or right-handed light get absorbed more than the other, or in emission, either left-handed or right-handed light emits more. In addition to the classical all-carbon helical molecules, here in this presentation, I would like to focus on heterohelicene. Hetero means something else. And in our study, we put heteroatom over here, represented as a star, to somewhere around here, so that the properties can be changed, varied, based on the heteroatoms we introduce over here. Helicene has been known since 1950s. It's really an old chemistry, and in addition to all carbon helicenes, it's been known like the oxygen can be incorporated, or the sulfur atoms, oxygen. Any various kinds of heteroatoms have been incorporated into the helical structure. In the synthesis, this sulfur-containing part are combined to give helical structure. Our approach started from this chemistry. That is, we happened to find synthetic pathway to close up here the two carbons with heteroatoms. The two carbons over here and here existed in bisphenanthol. Three benzene rings bound to another three benzene rings, and here are two hydroxy groups, phenols, and we could connect between these two. Let me start from oxygen and nitrogen. The first report, synthetic report, appeared from a group in 2005, already 16 years ago. This is a very simple natural product synthesis, and here the benzene OH and benzene OH was transferred to a triplet and then closed up to nitrogen. This moiety is called pyrrole. And when we were making this natural product using our palladium catalyst, our interest was this palladium catalyzed reaction. Then we found that instead of simply phenol, when we have 3 units over here and the 3 units behind, we can close this carbon and this carbon with the nitrogen so that this molecule can become helical. Also, we could make this helical molecule not by nitrogen but oxygen bound. The structure is so cool. This is single crystal X-ray analysis of this helical molecule having oxygen right here. As you can see the packing, this helical unit is stacking to the next one and the next one, so it's really like a spring structure. It was very nice to see this lovely packing, and but when we have nitrogen, the nitrogen had phenyl group, that's benzene ring over here. So we the packing was not as nice as the oxygen one. It's a bit more complicated packing structure. Anyway, currently this is still ongoing project, but we are interested in single molecule property of this helicene molecule. And we are collaborating with Dr. Kumagai in Fritz Haber Institute in Berlin to measure single molecule property. Like we are spreading the molecule onto the surface, like a silver 111 surface, to see very beautiful STM image. Actually, as you can see over here, there are a pair of compound nicely arranged, and here in this area the picture is a bit hazy, so we think this twin structure is coming from the two helical molecule, and this hazy area is coming from the benzene ring over here and here, which is perpendicular to the surface. We want to measure single molecule like conductivity or Raman spectrum, and that's what we are currently fighting against. Let me move to the next element, that is phosphorus. Again, starting from this 3+3 unit triplet, we could close it to phosphol, that is a 5-membered ring having phosphorus in it. Unfortunately, this phosphol is very sensitive to oxygen, so we decided to work on phosphol oxide instead of phosphol itself. Here the phosphorus atom is valency is 3, while this is 5 valent pentavalent phosphorus atom, phosphine oxide. Also, we could convert this oxygen to sulfur. So these are the molecules we enjoyed our chemistry. As you can see here, the oxygen, nitrogen, and phosphor oxide, these are shown here are the absorption and emission spectra. As you can see, there is clear difference. I mean, you can see for oxygen and nitrogen that we could see very clear fluorescence. On the other hand, and absorption spectra, the absorption edge was 388, 400, 390, about the same. But for the emission, oxygen and nitrogen showed fluorescence, 399, 419. But for this phosphor oxide, there was a significant Stokes shift, large red shift took place. So that, this is the Stokes shift. So something strange is going on at the excited state in this phosphor oxide. So we further went forward for DFT calculation. This is not the excited state. This is simply the calculation for HOMO and LUMO level. It's already 9 years ago, so the calculation was not that high in level. But anyway, the HOMO is simply located in the same way as for nitrogen. But in LUMO, for phosphor oxide, we did detect that there is something special going on this phosphor oxide. That is, for this phosphorus oxygen bond, there is a huge sigma star orbital. And for PC bond, again, there is a big sigma star orbital. And these two sigma star orbitals delocalized to the diene moiety, that's here, the butadiene moiety, and the terminal carbon, phosphorus and the sigma star, and this carbon, pi star. Pi star, sigma star, pi star does have delocalization so that this LUMO is very much stabilized. And this was the trick why we got so much huge Stokes shift. But more interestingly than simple absorption and emission, this is my favorite picture. That's crystal packing. This is a schematic drawing of the X-ray single crystal structure. As you can see, this is the helical moiety of this molecule, and benzene ring over here, and phosphor sulfide. The dipole moment is drawn here, and this vector is divided into perpendicular to the helical structure and parallel to the helical structure. As you can see, there is a canceling of this dipole moment. One molecule directs in this way and the next one directs in this way, so that this parallel vectors get canceled to each other one after another. On the other hand, in this column, the dipole is directed into one direction. Naturally, the neighboring column have this direction dipole, so that the neighboring two columns cancel to each other. That's really usual to cancel all the dipole to get packed crystal structure. However, what interested me is this column consists of only plus isomer, that's the helical structures clockwise, while this column consists of the minus isomer, the anti-clockwise helical structure. So this purple and blue are mirror image to each other and they never overlap, so they are different molecules. Interestingly, all columns having this direction dipole had clockwise plus helicity, while this column, all of these dipoles consisted of anti-clockwise structure. So if you we are very much interested in the structure and it could be applied for non-linearity. But other than that, if you have any sort of interest or application of this type of molecule, I would be very happy to collaborate with you. This is one way for plus isomer, and this is the other way around for the minus isomer, and these two are mirror images to each other. Okay, this is my group photo. It's so unfortunate that our group photo is not usual. I mean, usually we have a group photo, everybody together, but unfortunately, this time we can have only this type of photo. By the way, let's see, I sent you the home page of our website, information, just to give you image if you're interested in. Anyway, let me go back to my presentation. So, okay, so far, oops. As for this heterohelicene, I talked about nitrogen, oxygen, and phosphorus. The rest of my presentation will be focused on carbon, silicon, and ruthenium. Silicon and carbon. When we bridged the two carbon atoms with CH2 or Si dimethyl, C dimethyl, C diphenyl, we saw about this very much similar absorption over here, and it's quite different from helicene molecule, that is this carbon version. So when this is all carbon conjugated, the absorption and the emission are much longer redshifted. It's because of this conjugation, and the emission, quantum yield is quite low. On the other hand, when this conjugation is cut, is not when it's disconnected by carbon or silicon, sp3 atoms, we did see a very high quantum yield and very strong emission, especially in case of dimethylsilane. We did see very bright blue fluorescence of even in solid state. So we hope we can find some sort of application of this silicon-containing material utilizing this very strong blue light emission. Owing to the helical structure, We can also detect chiroptical properties. That is, the red and blue over here are CD spectrum. That is to differentiate right-handed and left-handed light absorption. And shown here are the emission spectrum. And for emission, we also saw that the silicon-containing material, which shows very strong emission, does have preference of either right-handed or left-handed light emission. The G values that's to evaluate the degree of handedness is not extremely high yet, but we were very happy to see this very strong emission together with reasonable G values. We also made double helicene. Actually, the synthesis was very difficult, and the key for our success was we could transfer the bromide to dilithiated compound. With this dilithiated aryl compound, we could put 1, 2, 3, 4 nucleophiles onto silicon tetrachloride. Fortunately, we could get tetra-arylation of silicon and could get this double helicene bridged by silicon. Actually, it turned out to be this is the first spiro. Spiro means the two rings are connected by the sp3 structure. We could make this spiro double helicene, not the conventional double helicene. Means conventional double helicene always are connected by the conjugated structure. That means the dipole of the two helicenes are parallel to each other. On the other hand, luckily, as we could connect them by spiral structure, the two dipoles are perpendicular to each other. And I will explain a little bit about what we obtained with this perpendicular arrangement. Compared to monohelicene, the double helicene showed much longer in absorption. That means the absorption get redshifted and emission too. We did see lovely fluorescence, but I would like to so the redshifts in absorption and fluorescence. I'm delighted to explain why we could get this redshift in the double helicene compared to monohelicene, because there is no conjugation. The two helical structures are perpendicular to each other, so there is no conjugation, seemingly, no pi conjugation. But silicon contributed to connect these two helical structures. So first, Silole is famous of low LUMO. Let me explain what the low LUMO means. Silole, silicon-containing pentadiene structure, can be divided into butadiene and silicon moiety. The orbital of butadiene, the LUMO orbital of butadiene, is drawn like this. Here is a node, here is another node. So this is the pi star orbital of butadiene. And for silicon moiety, carbon-silicon sigma bond has sigma star orbital located over here. For this carbon-silicon bond, the sigma star is located over here. And when these two are combined, we can have this, we have LUMO orbital where this blue part and the red parts have conjugation, and this white part and these two white part has conjugation to lower the LUMO. This is so-called pi star sigma star conjugation. As you can see, the sigma star and pi star, sigma star and pi star are conjugating to each other. The white part, sigma star, pi star are conjugating to each other. In addition, when the siloles are bound in a spiral structure, this part is conjugated, as I mentioned previously, sigma star, pi star. On this part, again, the sigma star, pi star conjugation does take place. But these are perpendicular to each other. And it could have been perpendicular means no further conjugation. However, luckily, due to helical structure, we did see the delocalization. Let me explain. So like I said, when the silole unit has perfectly perpendicular structure, then the orbitals are not overlapping at all. However, because the helical structure twists the silicon, so it's not perfectly perpendicular. It's a bit twisted. And because of this twist around the silicon, if you're looking, we are looking the structure from this direction. And these two orbitals are in front, and these two orbitals are at the top and the bottom. And as you can see, because of this twist originating from this steric demand of helical structure, the two are close to each other, and these two are close to each other. And when these two can overlap, it stabilizes the unoccupied molecule or orbital, while the other one has the opposite sign, so it's destabilized. And this is the reason for further stabilization of the LUMO orbital to cause redshift of the helical structure. We call it spiral conjugation, and we were very happy that we could see the spiral conjugation in the spiral structure. And we did see chiroptical properties too. Let me finish my talk by explaining about our carbon ruthenium chemistry. Means the main structure itself is carbon, but when this proton is abstracted, this 5-membered ring becomes anion -1 carbon anion, and it gets bound onto ruthenium. The ruthenium is sandwiched with the two carbon planes. It's called metallocene. There is a report having this metallocene type structure, but only 1, 2, 3, 4, 5 was reported, but no report for the 7 rings. And as 5 is too short, the ring can flip each other and it cannot be a stable helicene. But as we have more, we have 7, this structure is a very stable helical structure. We could even make double helicenes bound by metal. So this carbon metal bond is really flexible. 2 helix can rotate around ruthenium. So it's bound onto the metal, but the rotation is really free. And we can have plus plus or minus minus or plus minus. Fortunately, we could separate all these plus plus and minus minus and plus minus. Yeah, I like this structure, ruthenium bound. So ruthenium purple is underneath here, and this helix and this helix are connected at the central position, and it can just rotate around. When we, instead of having two helices on one ruthenium, when we added two equivalent of ruthenium to one helicene, we could see another compound. That is, one ruthenium is bound underneath this helical structure, and the other ruthenium is bound on above the helical structure. So two rutheniums are bound onto one helicene. This is 5-membered ring, this is a 6-membered ring, but nevertheless, ruthenium are bound on here and here. Interestingly, we found there is a metal to ligand metal charge transfer in excitation. As you can see, this is the S0, that's the ground state. And upon excitation, the singlet state is made of the ruthenium and the so the ground state is located on this part, on this ruthenium. But upon excitation, the electron get excited to the ligand part plus the metal orbital. So this is from metal to ligand metal orbital charge transfer, electron excitation. That means this bottom ruthenium is the electron donor and the top ruthenium is the electron acceptor. Interestingly, we detected phosphorescence, not a simple not a simple fluorescence, but we detected phosphorescence of this molecule, both in solution and in solid state. So the T1 was calculated to be over here, and it came down to S0. That means coming from this metal center back to this metal center. So upon excitation, it goes, the electron moves from this ruthenium to here, and in emission, the electron comes back from this ruthenium to this ruthenium. We are not the only ones working on multi-metallic helical molecules. So if you are interested in, you are guided to see the publication from Katz and Castle and Mizuri, and there are even more publications working in being interested in physical properties of the double helices. Okay, so that's all what I wanted to share with you, and these are the people I deeply appreciate. And if you have never come to Tokyo, please do so once you can travel easily. Not at this time probably, but hopefully soon. It's a big city, yes, but there are many lovely places to visit. And also our university, this is the main clock tower, and this is our building. We also have a beautiful campus, including very much historical places like the Red Gate and the lovely Japanese style garden. So all of you are welcome. And finally, thank you very much for the invitation again, and thank you for listening.
Hello, madam.
Yes. Hope you
Thank you very
enjoyed.
much for the wonderful talk. Yeah, yes. Thank you very much for the wonderful talk. And I have a couple of questions on the chat box, and let me read it. And before that, I have a personal question.
Yes.
In the monohelicene studies that you reported in the very last about coupling ruthenium,
Mhm.
so is there any study on coupling iridium instead of ruthenium?
We made only ruthenium and iron, but have never worked on iridium yet. The valency is a bit different.
Okay.
So ruthenium and iron 2 we could work on, but iridium either 1 or 3, it's still ongoing. But yes, of course, iridium is the most popular metal for phosphorescence. That's true.
Yes. So then, so one more question, and you put your heterohelicene on silver 111 surface. Is there any reason for the choice to put the molecule on the silver atom?
We tried gold, silver, and copper, and turned out to be silver was the best one to hold our helical molecule.
Okay. Anything related to the lattice parameter of silver or?
And actually, I'm not the specialist, and just my our collaborator selected
I see.
it, and I know that my student visited Germany to try everything, and he could get it. That's all I know. Sorry for that.
No, that's okay. Just out of curiosity, because we also worked on
Mm-hmm.
silver 111 surface. So,
Okay.
and there were a couple of questions on the chat box, and let me read one
Okay.
by one. And if you maybe you could comment on it. And one student asked, "Is
Mhm.
what are the applications of circularly polarized fluorescence that you
I
mentioned at the
see.
beginning of your talk?"
Right.
Yeah.
So CPL, people say that CPL can have further information. So instead of like color, you can have one additional information depending on plus or minus to like when you print uh, bills, notes, money.
Yes. Yeah.
If you use this color, it's obvious that under certain detection, you can see whether this note is real or not. But I don't know exactly whether this is really applicable or not, but this is what I heard. So, the
I
answer
see.
is there is one more information when it's
Yes.
printed.
Okay. Thank you. And another question: is there any nonlinear optical studies that you have done on these molecules?
No, not yet. The phosphor oxide, which arranges nicely the anti-parallel columnar structure, we tried to collaborate with physicists, but their request was first grow at least 3 millimeter cubic crystal. And this was the bottleneck. We could not grow our crystal that large. So still not yet.
Okay, fine. And also, you were speaking about the effect of phosphorus. I mean, you noticed a stock shift.
Mm-hmm.
Yes.
Yes.
And did you notice this kind of effect in double helicenes as well?
Yes. So, like I said, the phosphor oxide has the sigma star orbital of carbon phosphorus and oxygen phosphorus. So, the same thing happens for carbon silicon in Silole. So, in this silicon and phosphorus, we did see the sigma star pi star conjugation, and it contributed a
I
lot
see.
to lower the LUMO for the redshift. Yes.
Okay. And also one very general question.
Yes.
So I'll read the question. In photonics, we may do some experiments related to dye-sensitized solar cells. So for which we need to select the matching of HOMO-LUMO band gap. So before experiments, how can we select this matching? is there any criteria other than theoretical predictions?
In theoretical prediction.
No, theoretical.
Elec-
Yes. Other than theoretical prediction, do you have any options to predict through experimental guess? I mean, the HOMO,
I
LUMO
see.
levels.
Okay, okay. So when the molecules are main group molecules, recently theoretical prediction is getting a reasonable result, but this is but this is mostly the HOMO LUMO for ground state. For excited state,
Yes,
I think for excited state, I think the theoretical approach is not as good as for the ground state. And one of my student is trying to apply machine learning.
Yes,
So
that's what I would think.
Yeah, he just collected when he had to stay because of COVID. He just get connected to all the literature to dig the data and went for machine learning, and I think seems like it's working very well.
Yes, it's quite powerful. Yes,
indeed,
yes. And what about the stability of these molecules? Actually,
most of the molecules are stable. At least even the ruthenium one, it depends on what the definition of stable, but even the ruthenium one, we could vaporize for chemical deposition onto the surface. So it's reasonably unstable, I think.
I see. Okay. So those were the questions. And I would like to thank you once again for sparing some time for us. And thank you very much for joining us today. Thank you, madam. Thank you.
Yeah.
So
thank you so much.
I will tell I will tell the participants to contact you if they have any specific queries related to the talk later on.
Okay. Just visit our homepage and my email address is
Sure.
Okay. All right. Thank you so much.
Yes. Thank you, madam. Thank you.
Bye-bye.
Yes, thank you. Thank you all. Bye.